Okay, let's dive right in. We are looking at an epic structural showdown today between two fundamentally opposed views of our digital reality. And honestly, we aren't just talking about some abstract ivory tower math here. This battle is literally dictating the entire future of artificial intelligence. Down one path, we have the fluid, probabilistic quantum wave. It's a world built entirely on approximation and, well, guessing. But down the other path, we have the exact, unyielding deterministic integer, a world of absolute proof. So, welcome to The Explainer, where today we are unpacking a massive architectural crossroads that will determine whether our machines serve us verifiable truth or just highly educated guesses. We're basically standing at a literal fork in the road of computational philosophy. Down the first path, we follow Professor Moriarty into the realm of classical physics. Here, quantum mechanics is defined by statistical probability. It's quite literally about adding up waves in just the right way. It's fluid, it's continuous. But then, look down the opposing path. Here we have Kyle MacLean Smith's pursuit of absolute mathematical truth. In Smith's world, 1 + 1 equals exactly 2, every single time. There are absolutely no hidden seed tables, no approximations, and zero guesswork. It is the ultimate structural foil to the quantum approach. So, here is our roadmap for today's intellectual duel. We'll quickly map out these two competing paths, dive deep into the quantum wave reality, and then explore this impending vanishing point crisis. From there, we'll look at how the deterministic integer engine offers a radical solution, exactly how to shatter the trig wall, and finally, we'll wrap up with the profound philosophy of Hassiatate and digital physics. Section 1. Two paths of computing. Let's start by exposing the hidden reality of how our machines actually process information. You see, our entire digital framework right now is teetering between two extreme paradigms. On one hand, we've got a continuous space of probabilities, a system relying heavily on lossy mathematical approximations, which is really just a fancy way of saying it's guessing. On the other hand, we have discrete, absolute mathematical certainty, a system that is perfectly rigid and entirely forensically accountable. Now, you might be wondering, why does this teeter-totter actually matter? Well, because every single time your bank processes a transaction or an AI makes a critical medical diagnosis, it relies on this exact underlying math. We're at a pivot point right now between demanding undeniable, exact digital receipts and just settling for fluid, often flawed approximations. Moving to Section 2, the quantum wave reality. First, we really need to explore this continuous, fluid world of quantum mechanics, beautifully detailed in our sources by Professor Moriarty. Professor Moriarty does a brilliant job of stripping away all that sci-fi mystique around superposition. We aren't talking about bizarre parallel universes or infinite alternate realities here. It's actually so much more grounded than that. It's simply about waves interacting and interfering. The process breaks complex patterns down into continuous Fourier sine and cosine waves, and then sums them all up. When those waves align perfectly, you get constructive interference, which builds the signal. When they clash, you get destructive interference, canceling it out. And this pure, continuous wave mechanics, that forms the absolute baseline of our current probabilistic paradigm. But here's the catch. Because this quantum processing is entirely probabilistic, you can't just run an equation once and get a definitive, hard fact. No, you have to pay a massive repetition tax. You prepare the system, you let those Fourier waves interfere, you measure the result, which automatically collapses the wave function, and then you have to repeat that entire process from scratch, over and over and over again. The machine has to do all of this incredibly heavy computational lifting just to extract a statistical average. The foundation here is probability, not a single exact answer. Section 3, the vanishing point crisis. So, what happens when we rely on those probabilities and approximations for critical tasks that actually require exactness? This brings us to a massive systemic problem. Kyle MacLean Smith warns us about a phenomenon he calls the FPU gambler. See, inside a modern processor, the floating point unit, or FPU, has a fundamental tendency to round off and guess. When you build complex systems on top of these lossy approximations, you crash headfirst into what Smith defines as vanishing point probabilities. This is the mathematical certainty that microscopic errors in an FPU don't just stay flat. They compound infinitely. Imagine dumping all your data into a blender. It creates this lossy digital smoothie where the original data's specific identity gets permanently wiped out, almost like going through a digital wood chipper. And once it's blended, you can never unblend it. The original truth is just gone. So the crucial question we have to ask is this: what happens when a machine starts learning from degraded copies of copies? Think about the AI systems we are all using today. If an AI trains on synthetic data, meaning data produced by another AI using these exact same guessing mechanisms, we cross a very dangerous 50% critical threshold. The mathematical errors compound aggressively and completely irreversibly. This leads directly to total semantic collapse. In fact, it is the exact structural root of the AI hallucinations we hear so much about right now, where the machine just confidently invents absolute nonsense because its underlying mathematical truth has literally been blended away. Which leads us to Section 4, the deterministic integer engine. To counter this impending crisis of probabilistic noise, Smith introduces a starkly opposite radical paradigm. We are talking about a monumental structural shift here. To escape that digital smoothie, Smith proposes moving completely away from continuous Fourier waves and that guessing floating point unit. Instead, he shifts the core mathematical workload directly over to the arithmetic logic unit, or ALU. By forcing the system to use discrete integer logic, we establish absolute physical certainty. This is exactly how you unblend the smoothie. You replace the gambler with an unyielding, rock-solid mathematical ledger. This rigorous ALU framework fires probabilistic guesswork out of the runtime loop entirely, and by doing this, it completely eliminates runtime variance. That means 1 + 1 equals exactly 2 on every single CPU on Earth, every single time. But even more profoundly, this restores Noether's theorem of reversibility to computing. Because everything is an exact integer, you can forensically trace every single action back to an exact, auditable line of code. It prevents that wood chipper effect entirely, grounding artificial intelligence in a highly verifiable, FDA-ready reality. And when we say FDA-ready, we literally mean code that is so utterly traceable, irreversible, and exact that it could easily pass the most rigorous life-or-death regulatory audits. Section 5, Shattering the Trig Wall. Okay, so here's the ultimate engineering challenge. How do we actually force these chaotic, fluid AI algorithms to operate with this flawless integer rigidity? Smith's solution is found within his LNS architecture, specifically a really fascinating concept called the spectral alpha fan. This system completely abandons spatial approximation. Instead of floating around and guessing where things are using continuous waves, the architecture moves beyond the polar wall to rely on absolute integer geometric rigor. Just imagine a grid where every single line, every single intersection is a bit-perfect map of discrete rational coordinates. There is no rounding, there is no guessing, there is only exact mathematical location. But how does it actually pull that off? Well, it does this through a brilliant concept called Seidel normalization. You see, traditional AI relies on really heavy trigonometry, things like cosine scoring to function. But trigonometric curves are incredibly messy. They literally force the processor to guess and round off, creating a massive, power-hungry computational barrier known as the trig wall. Seidel normalization completely shatters this wall. It anchors the entire coordinate system so that side A always equals exactly 1. By doing this, it turns those messy, power-hungry curves into perfectly straight, exact, discrete lines. It employs a technique called the squaring strike, which effectively freezes all that liquid, continuous potential into a bit-perfect Pythagorean integer hub. You get all the geometric relationships you need for AI, but with absolutely zero precision debt. It is mathematically flawless. Section 6, Heikelcitate and digital physics. But, ultimately, controlling the machine requires way more than just flawless mathematical code. It demands a profound philosophical grounding. And that brings us to a massive, foundational concept highlighted in the sources, Heikelcity universale. Now, Heikelcity translates roughly to the absolute thisness of an event. It is the philosophical guarantee that an event happened exactly here, exactly now, and was authored by a specific, localized human being. In Smith's framework, this localized human effort is essential because it forms an undeniable semiotic bridge directly to the machine. It ensures that human agency remains the immutable anchor of the whole system, which fundamentally prevents the machine from drifting off into automated hallucination. Under the sovereign protocol, you absolutely cannot separate the mission from the physical record. It's really a perfect partnership. On one side, the human acts as the sovereign pilot, providing the messy, associative, and highly creative strategic intent. The compiler then translates this intent into a rigid, deterministic script. And finally, the agent cell acts as the unyielding engine, executing all the tedious sweat using relentless, unforgiving ALU logic. The result of this entire chain: total forensic accountability, and a completely irreversible physical realization of human intent. So, as we wrap up this explainer, we find ourselves standing right at the crossroads of probabilistic quantum noise on one side and bit-perfect deterministic fidelity on the other. And it really leaves us with this final, incredibly provocative thought. If we stop actively writing that deterministic bridge ourselves, if we simply surrender our human intent to a guessing automated machine, who actually controls the physics of our digital reality? It's definitely something we all need to be thinking about. Thanks for joining me on this explainer, and keep questioning the limits of what we can compute.